Imagine a sweltering summer day where one neighborhood feels like an oven, while just a few miles away, another area is noticeably cooler. This isn't just a feeling, it's a real and dangerous phenomenon. Heat is the deadliest weather event in the United States, killing more people annually than hurricanes, floods, and tornadoes combined. So, why are cities dramatically hotter than the surrounding countryside? And who pays the price when urban heat becomes deadly? Everything is a system. In grade 11, we're exploring how the built environment of our cities creates a feedback loop that traps heat, intensifying a phenomenon known as the urban heat island effect. Understanding this system is crucial for designing cooler, healthier urban spaces. Urban climatologist Dr. Anya Sharma explains that cities become heat islands due to several interacting factors. Dark surfaces like asphalt and rooftops absorb up to 95% of solar radiation, converting it into stored heat, which dramatically increases the surface heat absorption rate. Meanwhile, vehicles, air conditioning, and industrial processes release waste heat generation directly into the atmosphere. Crucially, replacing natural vegetation with concrete drastically reduces the evapotranspiration cooling rate, eliminating nature's built-in air conditioning. These components work together to raise the ambient air temperature across the city. Our model of the urban heat island effect has 6 key components. The single external input to this system is urban land cover composition, which describes how much of a city is covered by buildings and pavement versus green spaces. The internal outputs are surface heat absorption rate, waste heat generation, evapotranspiration cooling rate, ambient air temperature, and the critical heat-related health impact. Let's trace how these components interact. A positive relationship means more urban land cover composition by impervious surfaces leads to a higher surface heat absorption rate. Conversely, there's a negative relationship between impervious surfaces and the evapotranspiration cooling rate, because less vegetation means less natural cooling. Both a higher surface heat absorption rate and increased waste heat generation have a positive relationship with ambient air temperature, making the air hotter. Finally, a positive relationship exists where higher ambient air temperature leads to a greater heat-related health impact, especially for vulnerable populations who often live in the hottest neighborhoods. Build your heat island effect model to explore solutions. What if we mandate cool roofs and permeable pavements across an entire district? How much would adding 1,000 new trees to a neighborhood reduce its peak temperatures and improve health outcomes? Careers in urban climate science and planning are vital for addressing heat islands. Urban climate scientists earning $70,000 to $130,000 annually use data to map heat vulnerability and design cooling strategies. Environmental justice planners making $60,000 to $120,000 per year focus on creating equitable climate adaptation plans for underserved communities. Everything is a system. Model it, build it, simulate it, understand it. Visit ModelIt T12.com.